Okay, Assalamu alaikum. Good morning, everybody. Let's continue on what we started last time. Much of the material that I am going to present today, we have come across last time. Last time, just we went through the laminar and turbulent characteristics of the flow, and we came across Reynolds number that you already did take in fluid mechanics. Now we will continue on that. Now this presentation, it's 49 slides, by the way. We'll try to finish as much as we can today, and inshallah next Sunday will come to its end. But this presentation mainly talks about how to quantify the friction factor F. So this is the whole thing of this thing, and you already did take in the fluid mechanics class that F for laminar flow relates with Reynolds number, and you already came across a situation that F changes according to the flow type. For laminar, it is something different than that for turbulent. So the whole presentation will really come across that. The thing that you already did take in fluid mechanics will not really waste time on it, and the new stuff that we didn't yet get, which is for turbulent, maybe we can spend more time on that. Let's get back to the PowerPoint presentation. And again, this presentation, in its way to describe the variability of the friction factor, will come across the velocity profiles. What's meant by profile, by the way? When we say profile, variation. So the variation of the velocity with distance. But here we are talking about with the radius, or with the radial distance from the center line of the pipe. And the other thing is we are going to develop the equations that relate the friction factor with the velocity or whatever other characteristics. You already know that fact because we already said that in the first lecture, that shear stress creates friction, and friction in the end is a loss of energy, and this energy must be quantified. Now this loss in energy must be quantified. Why? Why we must quantify the head loss? ليش لازم نقيم رقميا قيمة الفاقد في الانرجي? Why?
Determine efficiency of our pump or turbine or something.
No.
Important.
No. You can say it in a different way. We can tell what would be the energy that will be for the water that will arrive at a final point. So we can tell, for example, we started, as you know, with the energy conservation equation. Let's just memorize that, refresh that. H1 equals H2 plus head loss. And if we look at a pipe like that, this is point 1, as we said last time, this is point 2, and the head loss across the pipe. So if you know the head at location 2 from the head loss, then you can tell what is the pressure head. This is what we need mainly, the pressure head to know. This is the first thing. Now if we imagine a situation like that, there's a pump, this is ground surface, so this is like a wadi, this is at top of a mountain, we have a village at the top, but the source in the bottom. Now you would like to pump the water all the way, for example, up to this location. You must know the head loss through the pipe. Now, in order to know what is the right capacity of the pump, so this will help us to choose the right pump. So this is the way to say, not like what you have already said. Now, this head loss, you know, we said also that in the first lecture, depends on many characteristics, depends on the viscosity. Quickly, what would be the impact of viscosity on the head loss? As viscosity increases, the head loss increases. Why? Because it will be difficult to move, to drive the fluid. Yeah, so it's easier to pump water than to pump honey, oil, mercury, whatever. Flow conditions like velocity. If the velocity is high, the head loss higher. Why? But why? We know. Now, we know as the velocity increases, the head loss increases. First of all, why we know that? And why this is the case? Because if you write Darcy-Weisbach equation, so increase V, the head loss increases. But conceptually, why? Please.
بده يصير تصادم بين حركة الجزيئات الفلويد.
Yeah, and we can expect more head loss because of the internal activities in the water molecules. This is one thing. But if we think more, now the velocity equals what? QIA. Now, if we increase V, or V increases because the flow increases. Now, the area is constant. Because we are talking about a pipe. Now, the point is, it will be more costly. It will cost more energy to drive a larger flow rate. Yeah, you can imagine. You can put one person in a car. It will not really consume fuel as putting 5 persons. It will consume more because there will be more load on the motor, and it's the same. You drive more water, then you have to consume more energy. Simple as that. The geometry. What is meant by geometry? Shakl, the shape. Now, circular pipe will have a different head loss than square pipe. Back, if you look at this, for example, this is circular pipe, and we can imagine a pipe that has this cross section. Both has the same area, by the way, but I would expect that this might have less head loss than this, because we have here corner edges, rough edges, and this might really create edges and so on. Or you can imagine geometry like that, as in terms of the size. So this is 1 and this is 2. Head loss in case 1 is larger than head loss in case 2. So there are lots of things like that. And the last thing is the material of the pipe itself, or the roughness, and this is what is hidden in the term F in the equation that we already did write. Yeah, as the viscosity increases, yeah, يعني كل ما زادت اللزوجة بصير وكأنه الفلويد أصعب تحركه، يعني لزج أكثر. Yeah? يعني لما a very good example مثلا الكاتشب لما تطلعه من الثلاجة you need to shake it عشان تعمل deformation وتقدر تتغلب على قوة اللزوجة اللي موجودة في الكاتشب نفسه. لكن المي ما بيلزم شيء زي ذلك لأنه بفرط هيك. إذا بتحط نشا على المي بتغير الوضع. اللي بيعملوا الشاكرية باللبن والأشياء هذه يعني. هذا تسجل على كلنا. أوكي.
الرفنس لها علاقة بالهيدلوس؟
إيه؟
الرفنس لها علاقة بالهيدلوس؟
طبعا شو الرفنس؟ ايش معنى رفنس بالعربي؟ خشونة. اكيد يعني حركة المي على سطح خشن. اكيد يعني انت امشي بشارع وامشي بطريق وعرة. Absolutely you will get more tired in the second case compared to the first case. Anyhow. فإذا هذا already I think should be fine. Already برضو we said last time about the energy loss and its relationship with the piezometric head or the change in piezometric head. And we said this is only correct. The change in what is piezometric head? Without v square over 2g. If this is uniform, then the velocity is constant. Then it will drop down from the energy conservation equation. It will be right to say that head loss equals delta p over gamma plus delta z. Now, if this pipe horizontally, then delta z is 0. And only we have just delta p over gamma. Simple as that. And already we have already said that. We also came across these two equations. The first one you did take in fluid mechanics. The second one is HF over L, which is SF multiplied by gamma multiplied by the hydraulic radius. We talked about the hydraulic radius, will equal the boundary shear stress. So boundary shear stress equal gamma, the slope of the either hydraulic grade line in case of uniform flow or the total the slope of the total energy line in case of the general case multiplied by the hydraulic radius. Now let's take the following examples, and these are good examples because it tries to strengthen the concepts that you came across, but it's a very good entrance to the course itself. A horizontal pipe. So the first thing we need to think of the word horizontal. Horizontal means delta z equals 0 immediately. 0.3 meter in diameter. So this is D. Horizontal pipe means this is a pipe, this is the center line generally. We can say, for example, this is my datum. Datum generally is the mean sea level, مستوى سطح البحر. So we can say this is Z1 and this is Z2. Has an available pressure drop. Now water moved from point 1 to point 2, and in order for this movement to happen, we can say two things. There must be a pressure at point 1 that is larger than the pressure at point 2 by this amount. Or we can say it in a better way. For water to reach point 2, it will lose a pressure by 100 Newton per square meter. So we can say it in two different ways. But all the time, we must have a higher pressure at point 1 than point 2. Now, why I am not saying a higher total head? For two reasons. Again, generally, don't make that mistake. Generally, we must say H1 larger than H2. And the head loss is the difference. But because this is horizontal, then we dropped delta Z. And because this is uniform, then we dropped the change in the kinematic head. So it is right to say now it's a drop in pressure or pressure head. Now, this represents the change in the pressure. To drive a flow, then it gave me Q. Across through a length of 100 L. what shear stress will be developed on the pipe boundary? Yes, downward by this flow condition. So we can think of two equations. Either you can say one way, and you can just only memorize this one, or you can just immediately say tau 0 equals gamma RH multiplied by HL over L. So both will work fine. Now, this is the starting point. Now, for this to equal HL by gamma. So HL now will equal delta H. Yeah. Just that delta H, because later on, this is the only place in this course we will say delta H or HL equal delta P. Only this lecture only. But in the course, when we talk about water distribution networks, no. The head loss is the change in delta H. So I would like to write it in the general form, and then we say it's now this is over gamma. Again, for the two conditions, uniform and horizontal pipe. Other than that, this is wrong. And thus, it will equal the 100 over gamma. What is gamma? Newton per cubic meter, and that is Newton per square meter, so it will give me a value. Regardless what is the value, it's not really much important now. So this would be my head loss. L, you have it. The hydraulic radius, we said last time, yeah, D over 4. Now, I don't want anybody to go and say the area over the weighted per meter. No, just immediately put it D over 4. And gamma, it's rho G. Or, as we already put it there, doesn't really matter, and that's it in the end. And so then you can find the boundary shear stress. You have the solution here. Let's take another example now. A trapezoidal channel is carrying water at normal depth. Now, we have a new word. I'm happy to have this example here because this is kind of an introduction to one of the chapters that we are going to come across in this course. Normal depth. And it's saying here channel. What is the first thing? The first thing you have to think of when you see the word channel? Not pressurized. The second thing, open from the top. This is very important. So if we are talking about trapezoidal, that means is trapezoidal. But I don't have an upper limit. Why is it important to say we don't have an upper limit? Hydraulic radius. I mean, in the hydraulic radius, this will be affected by only the weighted per meter. The cross-sectional area does not really change. But the weighted per meter, اللي هو المحيط المبلل بتغير. Yeah, 3 edges, not 4. So I will do a different color to indicate that this is the water. Okay, should be. Now, this is the first thing. The second thing is the word normal. Normal means this is a uniform depth. So wherever, now this is, by the way, a longitudinal perspective section, that you are standing like this and the flow is going this way. We are not really having a side view yet. So the normal depth is the uniform depth. That is, this distance is 5.2 feet. The channel has a bottom width of 10 feet. So this distance (10 feet), and side slopes of 2 horizontal, 1 vertical. That means this is 2, 1. What does that mean? Yeah, or we can say it the opposite. For 1 foot of water depth in the vertical dimension, there will be extent of 2 feet. That means if I do like that, now this 5.2, and then this will be 10.4. Okay, and the other side is the same because this is symmetrical. It is running the channel on a slope of 0.005 feet per feet. So no, not SF now. It's not SF. The channel. Now let's do now a side view. Okay, for a side view, first of all, this is, we can imagine the channel like that. It must have a slope. This is exaggerated. Okay, or we can just do it here like that. Now the channel, on top it there is the water, so, and just like that. Now this is the water surface, but this is the bed, the bottom of the channel, قعر الواد أو الأناية or whatever. Now, if this is a uniform flow, what we must have here for this to be a uniform flow? Eh? Now, this represents the free surface, سطح المي, وهذا البottom. Now, the velocity constant. The velocity equals Q over A. We agreed now that Q, to keep it aside. So the area. Where is the area here? مساحة المقطع هذا. الآن عشان مساحة المقطع هذا تكون constant، مش لازم يكون constant عندي. المستوى بالضبط هاي المسافة. عشان تكون هاي المسافة اللي هون. أنا بطلع side view now، مش longitudinal. معناته عشان يكون هذا constant، معناته 5.2 هي نفسها هنا. This is uniform. For velocity to be constant, the cross-sectional area must be constant. And the cross-sectional area of the flow will be constant only if the depth of the water in the channel will remain constant. Now, if this is the case, this blue line represents what? Yeah, it's parallel to the bed. So the slope of this line is the same as the slope of the bed. So the slope of the frictional surface is the same as the slope of the bed. Now it's correct to say it this way. Okay? So this represents S for the bed, the slope, but at the same time, which is again head loss over distance. Simple as that. So what will be the shear stress in pound per square foot exerted on the channel bed by this flow? Now we can say he wants this would equal gamma like that. This is the second equation that we already saw. You can start from the first equation, but we don't really need to waste time. Gamma rho g, so it's not an issue. SF given now, this one. The only thing now we need to find is the hydraulic radius. Let's see. Now, we have this situation. And we already said this is 10 feet. This is 10.4, absolutely not to scale. And this again, 10.4. This free surface, this is 5.2. Like that. Now we need to find the hydraulic radius. First, it's the area over the wetted perimeter. The area equals summation of the two bases. The first one is 10 and the second one is another 10, another 10.4, another 10.4. Fine. Multiplied by the height. Regardless what is the number, we don't really care for now. And this should be in square foot, by the way. Now, for the wetted perimeter, now we are talking about this surface. Okay, and that means we have 10 multiplied. This one is like this one. So it's 2 multiplied by exactly. Like that. Just you go back, you find hydraulic radius, you put it in that equation, and then you can get the value of the boundary shear stress. Now we can find the shear force on the, for example, bottom of the channel. How? By the area. So the area is 10, the width, and then you have to see for how long you would like to find that. Okay, so this is how it goes. So important just to note in this example two things: the word channel and the word normal. Without assuming a normal depth or uniform depth, then you can't really assume that the SF is 0.005. You can't really solve that equation. We will see, inshallah, in the chapter of the open channel, how you can really find the slope of the hydraulic grade line when it is not really under uniform assumptions. Let's see. This is the solution. By the way, you will notice that there are readily available formulas by which you can calculate the area and the weighted per meter based on, for example, the slope and whatever, but this is something we will come across when we talk in detail about the open channel. For now, you don't really need to understand what was meant by these two equations. Another good example and good really to look at, water is flowing in a 6-inch diameter pipe. Okay, now he says upward. That means water is moving this way. Now, if the question didn't say that water is moving upward, how can I really tell that water is going this way? The energy line is going this way. That means, what does that mean that the hydraulic grade line is going this way? Energy.
H1 equal أكبر من H2.
Yeah, that means H1 is larger than H2. Or, in a better way to say it, water all the time goes in the direction of losing head. So, if this is the case, that means this point is at a higher elevation than this point. That means this difference was lost or spent صرف for the movement or the transfer of water from point 1 to point 2. So there is no need, in fact, to say the word upward, by the way. So this is one thing. At a slope of 0.1 foot per foot, this is the slope of what? There's no channel here. This is pipe. So this is the slope of the pipe. Now, is it important to know that? First of all, what is meant by 0.1 foot per foot? Exactly. As you move, for example, 1 foot in the horizontal direction, you will go up 0.1 in the vertical direction. That means if this is a 1 kilometer length of a pipe, what will be the end elevation or end difference? 10% from that. That means 100 meters. Now, just another question. Is this a high slope or a low slope? Like you are an engineer. Do you think this is a high or low slope? No, it doesn't really matter. Slope is slope for small distance or large distance. But yeah, but no. 0.1. I'm talking about this. Yeah. Slope doesn't really matter. But my point is this a high, as an engineer in the practice? Is this a high or low slope? It depends. Now, if this is above surface, like this is a street, so the pipe here. No, this is not high. And you have a building. كيف راح يكون شكل الخط؟ عمودي واقف. طب هذا قديش السلوب تبعه هذا؟ كيف واحد؟ واحد ايش؟ انفينيتي. يعني هذا كل السلوب اللي انت ممكن تتخيله لسه هذا اكثر منه. So this is not really high. امتى when this slope is really high? When we imagine a system by gravity, but the flow will go, by the way, this way, not the other way. Now, if this is under gravity, that means if you install a wastewater pipe in the street and it goes for 1 kilometer, that means if you start at 0 depth, for example, you will end up at 100 meters. تقدر تتخيل حدا بينزل 100 متر عشان ينزل خط صرف صحي؟ It doesn't really matter. in the pressurized systems, we don't really care much about the slope. So why this question is giving us a slope value? Why?
عشان نحسب دلتا زد.
عشان نحسب delta z. Only, just because this is delta z. So to apply, now this is a different case from a previous case. This is still uniform, so you still can drop the v square over 2g, but here you can't really drop the change in elevation. So you must take it into consideration. The observed shear stress on the pipe is 0.975 pound force per square foot. So this is tau 0. Now, what is the slope of the hydraulic grade line? What is SF? And again, notice that this is parallel because the velocity does not really change. So it needs SF. Now we have, for example, we know this equation. So SF is equal like that. Now, for tau 0, it is given. So you have that one. This is and for the hydraulic radius, it gives you the d. So it's d over 4. But the d must be in foot. This is in inch. So over 12. So this is half foot. So this is the hydraulic radius in foot. Now, the specific weight, how much? 62.4. Please do not make that mistake and put whatever in Newton per cubic meter. So this is pound per cubic foot. Then you can find SF. Now, what is this? When you solve it at home, you must really get that number. What is the pressure drop per foot? Yeah, assume that this length sorry just one foot. So what is the pressure drop? Now, what we need to do is quite simple. Yeah. Now we have a situation. You remember it. That's fine. Let's write the energy conservation equation. So it's H1 equals H2 plus HL. H1 is equals plus, yeah, but let's write it Yeah, like that. Okay. Now, this cancels. Uniform. Yeah. There's a velocity, but they equal each other. Okay. Now, what we need to find is the pressure drop or the change in pressure. Doesn't really matter. So P1 minus P2 will equal plus now this is how much is this?
Slope multiplied by horizontal distance.
Yeah, and the horizontal distance is 1 foot. So this is 0.1. And if you notice, this is positive, yeah, because we are increasing the elevation. So that means we have a positive drop in pressure due to this amount. And this one, if you go back, .125. Eh? For per foot. Yeah. So this is 0.125, the SF. So we have to go back. And just let's plug here. So the answer would be and the unit foot. Now we have a few minutes before we conclude. I'm just really wasting some time on that because these are important concepts. After that, the whole material will collapse and we will be really faster than that. But I would like to make sure that this is quite clear for all of you. What does it mean, by the way, the drop in pressure, by the way, which is?
Delta V over gamma.
Now this is positive. That means we lost a positive amount of pressure. Yeah. Now, what does it mean 0.225?
Pressure one higher than
Every
Already we said that. Plus.
Loss?
But by the way,
every foot we move, we lose 2.225.
exactly. Every 1 foot we travel per distance of the pipe, we lose this amount of energy. What else can we say as well? This energy that was lost came from two sources.
Head loss.
The first source is this, and the second source is this one. To me, as an engineer, which one do I care about more? I mean, I do care about both.
Head loss.
The head loss. Why? What do I call this term? This is the change in topographic elevation. يعني هذا إشي موجود في الواقع أنا ما بقدر أعمل فيه إشي. هيك المطلوب يعني. لأنه أنت بتتخيل هو البايب كأنه بده يطلع على جبل. وأنت مددته بهذا الشكل بالنهاية يعني. بس أنت بدل ما تاخذ طوله كلياته أخذت قطعة معينة منه. بس مش أكثر من هيك. بس اللي بينطبق على 1 يونت من اللينث بينطبق على الطول كلياته. لأن ليش؟ لأنه كله لينير عندي. كيف عرفت إنه كل شيء عندي لينير؟ لينير من درجة أولى. وتشينج في التوبوغرافيك إليفيشن لينير. لأنه الإليفيشن مش عامل عندي هيك وهيك وبهذا الشكل. No. Just على المسطرة. So this is the difference in topographic elevation. But this is head loss. As an engineer, you can't control this. But you can control this. You can reduce this by زي ما حكينا في البداية putting a higher diameter, putting a newer pipe, smooth from inside, things like that. But you can't say I would like to move less flow, because you are requested مطلوب منك انك تمشي او توصل flow معين, so you can't also choose that as an option. We still have يعني هاي أمثلة بسيطة but it's very important to pay attention to.
طلب البريشر دروب بير فوت، لو ما طلبش بير فوت التغير بالزد بتتغير
مرة ثانية.
طلب بالسؤال وات از ذا بريشر دروب بير فوت، لو بقى ازيد من فوت يعني مش بير فوت واحد التغير بالزد بتغير ولا
طبعا اكيد اكيد. هلا التغير زد راح يتغير بس سلوب ما بتغير، بس سمبل از ذات. يعني اذا كان ل 10 فوت ما عاد بصير عندي واحد. لا اكيد اكيد. هلا والله دقيقة مش مشكلة. في عندي كمان مثال بتطلع عليه في البيت لأنه اوريدي محلول عندكم. I think this is straight forward، يعني صار تكرار للشيء اللي اوريدي حكيناه. في كمان مثال ثاني جيد بس تطلع عليه اللي هو ال variability of the shear stress with the pipe. Just keep in mind something. إنه if the pipe is in this way, this is the center line. هذا كله B، بينما هاي المسافة R half. الآن لما أنا أستخدم R small letter in the case R varies between 0 but less than uppercase R، معناته هون هيك.
تروح بين
بعكس Y من فوق لتحت. معناته لما اجي افكر ب shear stress كأشي بتغير linearly، معناته it will be maximum at the boundary when R equals R, and it will be minimal at zero value at the center line. And just this is what we need really to keep in mind here. Yeah, and this is the idea from this very equation. هاي في البيت بس نطلع عليها بشكل سريع. تاو تاو and that means gamma D over 4 HL over L, but I can say this is still gamma. D is 2R, R capital letter, so that will be R
over 2.
but this is again, but if this is tau at R,
R small.
yeah. So we are not bringing anything new in this regard. Next, on Sunday, we will speed up, inshallah, and we'll start immediately from here. This is something also you already did take, so we'll just pass through and try to finish, inshallah, this presentation, because the remainder of this is not really much important as the thing that already we came across. Up to this, we are done. If anybody has a question, I'm ready to answer. If not, then you are free to leave now.